Okay, so good evening everyone. I am Shivani Dhok and I welcome you all to the week 12 tutorial of this course titled Principles of Signals and Systems. So this is the last week content. Um, this is the tutorial corresponding to the last week, but there will be an additional tutorial on Sunday from 3 p.m. Yeah, I will be taking summary session. In that I'll be mostly recapitulating everything whatever we have covered. In case you have any doubts, please put them in the Q&A portal before 12 noon tomorrow. Anything posted after that I won't be taking up. So let's start with the recap of week 12 content. So this particular week was the simpler one compared to whatever we had discussed till date. And this is the last content, and we looked at two important concepts. The first one, sorry, hello. Yeah, okay. So this week we basically looked at two different concepts. The first one was the group and phase delay of a system, and after that we looked at how to realize the IIR system, or for that matter FIR system as well. Okay, so let us first look at what is this group and phase delay. So we know that any LTI system is characterized by an impulse response h of t. We have an input x of t and output y of t. And this group and phase delay are the concepts which are corresponding to the case when your x of t or input is essentially a pure sinusoid tone with, let's say, frequency as omega naught. So we say that when we transmit a particular signal, then this sinusoid we are able to see delays in the system. And yeah, there are two types of delays. One is phase delay and one is group delay. So the phase the phase delay it is defined as tau p of omega naught, which is minus phi omega naught upon omega naught. And group delay this is minus dd omega of phi of omega evaluated at omega equal to omega naught. And what is phi of omega? So this h of t will have a Fourier transform as capital H of omega, and this capital H of omega we can write as magnitude of h of omega into e power j phi of omega. So this phi of omega is essentially the angle of your h of omega for a given set of omega. When you have something like modulation, like you are mounting a particular signal over a carrier, and let's say you are having some sort of amplitude modulation over a single tone, the output of that system is generally given by y of t is equal to a magnitude of h of omega naught cos of omega m t minus tau g cos of omega naught t minus tau p. So this first term here is basically your message signal, and this is your carrier. So message signal is basically affected by your group delay, and your carrier is affected by the phase delay. Okay, so this is all that we looked at regarding your group and phase delay. Mostly this whatever equation we wrote here, this and these two formulas are sufficient to solve any sort of problems that you will get in this concept. Then we looked at system representations. So we looked at IIR representation. It is equivalently, or rather equivalently, we can get FIR representation as well. So what we said that, okay, and these representations, whatever we looked are for your discrete time systems. So your H of n is, let's say, the impulse response of your discrete time system with transfer function as H of z. So this is the z transform of your, sorry, yeah, this is the z transform of your system. And we had seen that for an LTI system, this H of z is nothing but y of z upon x of z. So once you are given an impulse response and its corresponding transfer function, this is your transfer function. Now, based on this transfer function, you want to realize this system. And what do you mean by realize? Realization means how will you physically model, or rather practically model, this system. And we looked at around 7 different forms of realizing this system. The first one was the simplest one, direct form 1. The second one was direct form 2, and this direct form 2 allowed or enabled us to reduce the number of adders and delay blocks. Then we looked at direct form 1 transpose, direct form transpose 2. Then we looked at cascaded form, parallel form 1, parallel form 2. So these are the 7 forms that we looked at. I'll take one example, I'll take two transfer functions, and we'll construct the system representations for all of these 7 forms for those 2 transfer functions. So things will get clearer when we will solve those examples. Okay. But main things regarding realization of this system is this is carried out using 3 main blocks. So we have 3 main, instead of blocks, I'll say components. The first one is your adder block. So you have an adder block. So if you have x1 of n, x2 of n, its output will be x1 of n plus x2 of n. The second one is your gain block, gain or multiplier. So this is something like this. So if you have input as x of n, the gain is k. K can be any positive or negative, positive negative constant. The output will be k into x of n. And the last thing is the most important one, that is delay block. It is represented by z inverse. So if you give input x of n, then this will give x of minus 1 as output. So these are the 3 main components that we'll be using for constructing any system representation, any of the 7 system representations. Okay. So that's all that was covered in this week. If you have any questions, then let me know. Otherwise, we'll move on to the questions that I've planned to cover today. Okay. Let's move on to the next, to the first question. So it says that the input to a channel is a bandpass signal It is obtained by linearly modulating a sinusoidal carrier with a single tone, and the output is given by y of t is equal to this. Find the group and phase delay. So this is basically of this form, and this omega naught was your carrier, this omega 1 m was your message signal, that is your single tone. So the single tone signal that we are referring to is basically corresponding to your omega m, and sinusoidal carrier corresponds to your omega naught. And in communication systems, your single tone message signal will have a low frequency, much low frequency compared to your carrier signal. So when we say that your y of t is some a cos omega m t minus tau g into cos of omega naught into t minus tau p. In this is your message part, and this is your message part, and this is your carrier part, and your omega m is much less than your omega naught. Okay, now what we'll do, we are given a particular output signal y of t here. So what is given to us? Given to us is y of t equal to 1 by 100 cos of 100 t minus 10 raised to minus 6 cos of 10 raised to 6 t minus 1.56. So what we'll do, we'll try to represent this given y of t in this particular form that we just saw. So to do that, what we can do, this 1 by 100 remains as it is. We have cos of, we'll take 100 common, t minus 10 raised to minus 6 by 100. It will give me 10 raised to minus 8 into cos of 10 raised to 6 common, t minus 1.56 into 10 raised to minus 6. Okay, now let's say this is equation 1 and this is equation 2. Just give me a moment. Yeah, okay. So now what we'll do, we'll compare equation 1 and equation 2. Let me add a page. Comparing equation 1 and equation 2, what do we get? Your a is equal to 100. So the first thing is your a is not 100, 1 by 100. Then your omega m will be the smaller quantity. So omega m, you have 100 here, and here you have 10 raised to 6. So your omega m will be smaller value of your 106. So omega m is 100. Then omega naught will be 10 raised to 6. Then you have your tau g, that is group delay. Tau g corresponds to the delay which is associated with your message signal. So that is 10 raised to minus 8. So this is equal to 10 raised to minus 8 seconds, or you can write it as 10 into 10 raised to minus 9 seconds, which is nothing but 10 nanoseconds. And the last thing is your phase delay. So phase delay is a delay associated with your carrier. So with carrier, you have 1.56 into 10 raised to minus 6. So this is nothing but, this is in seconds, so 1.56 microseconds. So this is what we wanted to find out, your group delay and your phase delay. Okay. Is it clear? Any questions? Okay. If not, then let me move on to the next question. Okay, so there is a typo here. So it says that find the group and phase delay for the following systems. So the first system given to us is, or the first system with impulse response is delta t minus t naught. So this is the system given to us. And what is the definition of your group delay? Or let me just write that first here. So how do you find your phase delay? I'll just repeat the definition. Tau p of omega naught is minus phi omega naught by omega naught. And group delay is your tau g of omega naught, which is equal to minus t d omega of phi of omega evaluated at omega equal to omega naught. And what is your phi of omega? Your phi of omega is nothing but angle of h of omega. What is given to us in this question is not capital H of omega. We are given the impulse response in time domain, which means first we need to get H of omega from my H of t. That is, we need to find the Fourier transform first. So the first system given to us, is H of t is equal to delta t minus t naught. And this, the Fourier transform of this signal, which is Fourier transform of delta t minus t naught, we have seen multiple times. We know that delta t has a Fourier transform as 1. So delta t minus t naught will have a Fourier transform as e power minus j 2 pi, e power minus j omega t naught. And this comes from the time shift property. Okay, so therefore h of omega is e power minus j omega t naught, or you can write it as e power j minus omega t naught. So magnitude of h of omega is 1, and phi of omega, which is angle of h of omega, is minus omega t naught. So this is already in polar form with magnitude as 1 and 2 e power j angle. So this is your angle of, or h of omega, or rather your phi of omega. So now let us first find out group delay. Let us first find out phase delay. Which is minus phi of omega naught by omega naught, which is minus of phi of omega naught is minus omega t naught. So minus omega naught t naught divided by omega naught. Omega naught gets cancelled, and what we are left with is t naught. And then we can find out the group delay. Which is minus t d omega phi of omega evaluated at omega equal to omega naught. So this is equal to minus d d omega of minus omega t naught at omega equal to omega naught. This derivative is basically minus of minus T naught evaluated at omega equal to omega naught. This is not a function of omega naught, so this is nothing but equal to T naught. So for this particular example, what do we get? We essentially get your group delay is equal to your phase delay, and these are not the functions or other function of omega naught. Is it clear? Now let us try to repeat the exercise for the second system that is given to us. So the second system given to us is e power minus t by rc u of t. Let me add a page. Okay. So this is the second system. So h of t is e power minus t by rc u of t. So this is equivalent e power minus at ut, and we have seen the Fourier transform of this is a very standard signal. This you should also start remembering. So Fourier transform of this when a is positive is given by j omega plus a. Okay, so only when a is positive, and that is the case here. Your RC is basically your resistor and capacitor value, which is going to be a positive quantity. So 1 by RC is again a positive quantity. So we can directly apply this particular result. So using this, your h of omega comes out to be equal to 1 over j omega plus a. Here a is what? A is 1 by RC. So now what is angle of h of omega? So angle of h of omega, which is your phi of omega, is basically angle of numerator minus angle of denominator. Numerator is 1, so the angle of 1 is 0, minus tan inverse of real part, that is, sorry, in imaginary part, divided by the real part, which is nothing but minus of tan inverse of omega r c. Okay, so what do we have? So we have phi of omega as minus tan inverse of omega r c. So now let us start with the group with the phase delay. This is minus phi omega naught by omega naught, which is equal to minus of minus tan inverse of omega naught rc divided by omega naught. So this is nothing but tan inverse of omega naught rc divided by omega naught. Next we can find out the phase delay, group delay. This is minus of d omega of phi of omega at so this is equal to minus d omega of minus tan inverse of omega RC evaluated at omega equal to omega naught. Derivative of tan inverse of theta is 1 by 1 plus theta square. So this comes out to be equal to 1 upon 1 plus omega RC whole square into derivative of omega tau g of omega naught is equal to RC divided by 1 plus omega naught square R square C square. This you can equivalently just write it as 1 by RC upon omega naught square plus 1 by R square C square. That's all. So now in this particular question, your group delay and your phase delays are completely different. And those, both of them depend on your frequency of frequency omega naught. That is the input frequency to your system. Okay, any questions? Okay, if not, then let me move on to the next question that I have planned to cover today. So now I switch gears and now I'll move on to the system representations or realizations. So the first question here says that represent this particular system or transfer function in its direct form 1 and direct form 2 representation. So let's start with the simplest ones, that is direct form 1. Okay. So before that, let us first expand it. So h of z is equal to 1 plus, or rather let me write it like this, y of z upon x of z, which is equal to 1 plus 2z inverse divided by 1 minus 3z inverse plus 2z to the power minus 2. Okay, so now I can write this as, I can cross multiply and I'll get y of z into 1 minus 3z inverse plus 2z to the power minus 2, which is 1 plus 2z inverse into x of z. Or I can simply write it as, therefore y of z is equal to x of z plus 2z inverse x of z plus 3z inverse y of z minus 2z to the power minus 2 y of z. What I did, I just multiplied this inside and shifted this to the right. Okay, now taking inverse z transform, what I get? Inverse z transform of y of z is y of n. Inverse z of x of z is x of n plus 2. Inverse z transform of z inverse x of z is nothing but x of n minus 1 plus 3 into y of n minus 1 minus 2 into y of n minus 2. So now with the help of this input output relationship, So with the help of this input output relationship, we are going to now do the representation. So what, I'll just rewrite this relationship. So y of n is equal to x of n plus 2 times x of n minus 1 plus 3 times y of n minus 1 minus 2 times y of n minus 2. So this is what we have. I'll just partition this in two parts and I'll use the same page to do both. So let us start with direct form 1. So what do we have? Basically, we get an input x of n So this is x of n. This particular point is x of n. Then with respect to x of n, you have one more term, that is 2 into x of n minus 1. So you have an x of n minus 1. How do we get x of n minus 1? With the help of the delay block. So you'll add a delay block, that is z inverse. This here you will get x of n minus 1. Now this x of n minus 1 has to be scaled by a factor of 2. So this gets scaled by a factor of 2. And then you add it with your x of n. So here you had x of 2 times x of n minus 1. Let me write it like this. Yeah, here you had 2 times x of n minus 1. Okay, so now at this particular point, what do you get? You get x of n plus 2 times x of n minus 1. So this is what we have. But now on the top of it, what do you have? You have, let's say you have y of n here. This is your output. And you are going to feed back this y of n's delayed responses. So what do you have? You have y of n minus 1. That will give you y. So this delay block will give you y of n minus 1. Then you also have a term of y of n minus 2. So here you get y of n minus 1, and output of this will give you y of n minus 2. Now this y of n minus 2 gets scaled by a factor of minus 2. Similarly, your y of n minus 1 gets scaled by a factor of 3. And these two get added. So now at this particular point, what do you get? You get y of n minus 1 into 3. And at this point, you get y of n minus 2 into minus 2. Right. So this particular point basically adds this and this signal. So you get you get 3 into y of n minus 1 plus minus 2 into y of n minus 2. That is exactly this second part, whatever we have. Now what do? You add this, that is this part, and you add this part, both of them. So you have an adder block here. You add this and this to get your output, y of n. Okay, so now this is your direct form 1 representation. Okay, now there is a trick of doing this. Another trick. If you look at your transfer function, your transfer function was something like this: h of z equal to 1 plus 2z inverse divided by 1 minus 3z inverse plus 2z to the power minus 2. So if you look at this particular part, this models your input. So you have a 1, this is this 1, x of n into 1. Then you have 2z inverse, so 2 into z inverse. So this particular branch gives you 2z inverse. And here you get 1 plus 2z inverse. Now similarly, this particular part models your denominator. So you have a 1 here, rather 1 here. Yeah, a 1 here. Then you have 1 minus 3z inverse, but instead of minus 3, you get a 3. So this is basically 1 minus 3z inverse and 1 plus 2z to the power minus 2. This particular part, so all of these three model this 2z to the power minus 2. So here the gain blocks will be basically negative of your denominator one by one, and the z inverse will determine where exactly you are going to place those delay blocks. And this particular part will model your numerator. So z inverse and the scaling applied to that z inverse. So now just by looking at this particular representation, you should be able to get back to your transfer function. So this is all about direct form 1 representation. Then you have the second representation, that is your direct form 2. So in direct form 2, what do? You realize that this system and this system both are like a cascade form of each other. Then we make use of the commutative property of your convolution, and we interchange these two systems. So instead of starting with this particular part, we start with this part. So you have your y of n, oh, sorry, you have your x of n. Then you reproduce this particular part. So you have a plus like this. Then you have delay blocks. Then you have a gain block of unit 3. And you have a gain block of -2 like this. And then you then after interchanging here, this part will be given here. So basically this point and this point are same, and so is this point. So what will you get? This is as it is. This will pull out a branch from here that will have a gain of 2, and this will get added here. That will give me output y of n. So this system you swapped with this particular system like this, and you realize that you can make use of common delays, and that just helps you to reduce the number of delay blocks that you have in your system. So this is your direct form 2 representation of the same system. So the number of adder blocks required to represent this particular system were 3. Here also you have 3 adder blocks. There is no reduction in number of adders, or there is no reduction in number of your gains, but the reduction that you get is in terms of the number of delays. That is not significant here because the number of or the order of your numerator and denominator polynomial of your transfer function is not much. But if let's say you have a 10 order filter, then let's say denominator and numerator both have 10 orders, then this system will also have 9 delay blocks. This is 10 delay blocks, and this system will also have 10 delay blocks. But if you use this particular direct form representation 2, you will have only 10 instead of the 20 delay blocks used for this direct form 1. Okay, now again you can make use of the transfer function. Now here you will for direct form 2 you will start with the denominator. You will take this 1, then z inverse -3. So -3 z inverse, and then you have z to the power -2 multiplied by 2. So this coefficient comes here with a negative sign. This coefficient comes here with a negative sign, and you add and feed it back. And here this particular part basically corresponds to your numerator. So you have z inverse into 2, and you have a 1 here. This one corresponds to this branch. Okay, is it clear? Any questions in direct form 1 and direct form 2 representation?
Oh, madam.
Yeah. Okay. If there are no questions here, then let's move on to the next one. So let us take the same system function or transfer function. And now, instead of using direct form 1, direct form 2, we'll take up direct form 1 transpose and direct form 2 transpose. For doing that, what do? We have this h of z, which is equal to your y of z into x of z. So you write this particular system as something like this. Y of z upon x of z, sorry, w of z upon x of z into y of z upon w of z. So you treat this as h1 of z and h2 of z, and your h of z is basically h1 of z cascaded with h2 of z. So let's do that now. So you have h of z as 1 plus 2z inverse upon 1 minus 3z inverse plus 2z to the power minus 2. So I'll write it as 1 upon 1 minus 3z inverse plus 2z to the power minus 2 into 1 plus 2z inverse. So this thing is basically my h1 of z, and this thing is basically my h2 of z. So let's start with h1 of z. So h1 of z is what? 1 upon 1 minus 3z inverse plus 2z to the power minus 2, which is equal to w of z upon x of z. So therefore your w of z is equal to x of z into 1 minus 3z inverse plus 2z to the power minus 2. So your w of n is nothing but x of n minus 3 times x of n minus 1 plus 2 times x of n minus 2. Okay. And your h2 of z, sorry, is y of z upon w of z, which is equal to 1 plus 2z inverse. So therefore y of z is equal to 1 plus 2z inverse. I think I made some mistake. No. No. Oh yeah, sorry. One second. Something is wrong here. Yeah, so you have x of z is equal to w of z into 1 minus 3z inverse plus 2z to the power minus 2. So you have x of n is equal to wn minus 3wn minus 1 plus 2wn minus 2. Now the output of this particular system is w of n. So I'll write everything in terms of w of n equal to something. So we get w of n equal to x of n plus 3 times w of n minus 1 minus 2 times w of n minus 2. Sorry. And the second term is y of z upon w of z. So this is equal to y of z equal to 1 plus 2z inverse into wz. So you get y of n equal to wn plus 2 times wn minus 1. So we have two equations. First one is wn is equal to x of n plus 3wn minus 1 minus 2wn minus 2. And the second one is y of n which is equal to Wn plus 2Wn minus 1. So again, with the help of these two expressions, what we are going to do is we are going to do the direct form 1 transpose and direct form 2 transpose. So this is direct form 1 transpose, and then we'll do direct form 2 transpose. So let's start with direct form 1. So the input to the system is your x of n. X of n gets added with something which is function of your Wn minus 1 and Wn minus 2. So let's say you have an intermediate output as Wn here. So this gets, first it gets multiplied by a factor of 3, and then it gets delayed by a factor of 1. Similarly, you have minus 2 z inverse like this, and then this is nothing but your Wn. So x of n plus 3z inverse minus 2z inverse into z inverse is nothing but your W of z. So this is your W of n. Then this W of n, okay, so this particular point is W of n. This is getting carried forward like this. So this is W of n, so this is also W of n. So now for y of n, you have W of n added with 2 times W of n minus 1. So you can take out a branch from here, multiply it by 2, add it with W of n, but now this should be delayed by 1 unit like this. So this is your y of n. So your y of n is W of n plus 2 times W of n minus 1. So this is basically your y of n, that is your direct form 1 transpose representation. Now, similar to the way in which we translated from direct form 1 to direct form 2, we can translate from direct form 1 transpose to direct form 2 transpose. In that, we need to first identify that this particular part and this particular part can be separated out, and you can swap them. So first we'll take up this particular thing. So you have an adder block, gain of 2, z inverse, like this. Okay, and then you have an output here like this. This is your y of n. You have an adder block here now. Now you multiply this by a factor of 3 like this. So this is basically your y of n minus 3 times y of n minus z inverse, which is the thing that you have in your output. You have minus 2 and a delay block. So this basically comes from here. Sorry. This basically comes from here. So by swapping this particular system and this particular system like this, and then combining your adder blocks and delay blocks. So now in this particular presentation, we are also able to cut down on number of adders along with the number of delays. So this is requiring less number of adders and less number of delays compared to your direct form 2 representation. Any questions? Okay, if no questions, then let me move on to the next one. So the next question says that find the cascaded representation of the same transfer function. So essentially what I'm going to do in today's class is to take two transfer functions and represent them in the all the 7 possible system realization forms and see how to construct the systems. Okay, so h of z is 1 plus 2z inverse upon 1 minus 3z inverse plus 2z inverse. And for representing it in cascaded form, we need to first write it in as h1z into h2z. So let's say I write it as 2z inverse upon, I can factorize the denominator as 1 minus z inverse into 1 minus 2z inverse. So I can write this as 1 plus 2z inverse upon 1 minus 2z inverse. Yes? Yeah?
Actually, in the denominator, I think it is 2z power minus 2, ma'am. I've written as 2
Yeah.
minus 1.
This one only, no?
Yes, ma'am. Yes, ma'am.
Yeah, thanks. Okay. Multiplied by 1 upon 1 minus z inverse. So this term here, let's say is h1 of z, and this one is h2 of z. Okay, what are we doing this, or why are we looking into this cascaded and parallel form representation? So many times what happens is you have small blocks of your systems available. So let's say you have a block of system available or manufactured which has this particular transfer function, and you have another one with this transfer function. Now with the help of your h1 of z and h2 of z, these two systems, you want to get a system that has this transfer function. So what will you do? You will just combine these two and connect them in series combination. That is your cascaded representation. So this parallel form and your cascaded form representation are basically the cases or the representations which will make use of the already available system blocks to construct a new system. So now for getting your h of z, what will you do? You will connect h1 of z and h2 of z in cascade like this. So let's start with h1 of this system. So you have h of z equal to 1 plus 2z inverse upon 1 minus 2z inverse upon 1 minus z inverse. So let us first start with this system, that is your h1 of z. So you have xn. I will do direct form 1 representation. Sorry, direct form 2 representation. So how do we do that? We first construct the denominator part. So you have a 1, you have a delay z inverse, and the denominator gain, but with a negative sign. I mean minus of your denominator gain. So 2 times. Like this. And then we'll start constructing the branches for numerator in this side. So you have a 1 here already, this one. And then you have 2 z inverse. So z inverse you already have, you have to multiply it by 2. And then add. So this is your H1Z. And output of this system is the input to the next system. So the next system, you will start with this 1. Then you have a Z inverse. And then you have a -1 here. So the Z inverse, since it is in denominator, we'll scale it by negative of it, like this. And this is your Y of n. So this particular part is your H2 of Z. And equivalently, this is your H of Z. For realizing H1 of Z and H2 of Z, what we have used? We have used direct form 2 representation. Is it clear? Any questions?
Ma'am, excuse me, ma'am.
Sorry, yeah.
Only one doubt. Actually,
Huh?
if you are giving the multiplication factor, if it is -1, we need to include -1, no, ma'am.
Where?
Actually, in the delay block below that, we have included the multiplication factor, right,
Here.
ma'am? Yes, ma'am. Yes, ma'am.
It
In
is
that
in
case,
denominator.
okay. If it is negative, we are indicating it as positive, ma'am.
1 second. You have H2 of Z, which is equal to 1 upon 1 minus Z inverse. Okay.
Yes, ma'am.
Now let's say this is Y2 of Z upon, so it's Y of Z, and 1 second. And let's say output of this signal here is, let's say, your W of n. So this is input to the second system with transfer function H2 of Z. So this is W of Z. Okay. So
Okay.
now if I cross multiply, you have W of Z, which is equal to Y of Z into 1 minus Z inverse.
Okay.
Right. So W of n, which is your input, equal to Y of n minus Z inverse, which is basically Y of n minus 1. Now your output is Y of n, so you can write it as Y of n equal to Wn plus Y of n minus 1. Now you want to realize this particular system. Your input is W of n and your output is Y of n. And how do you construct it? You take your W of n and add a delayed version of your Y of n to it. So you delay your Y of n. That will give you a Y of n minus 1. And then you are scaling it by a factor of what? 1. And add it. Does that make sense now?
Yes, ma'am. Yes, ma'am. The same case for
Yeah,
H1 of Z also, ma'am.
correct. See, now here you have it in denominator, right? So the first
Okay.
block here corresponds to your denominator part. So you take this particular part corresponds to your 1. Now you take this, you delay it by 1 unit and scale it by negative of your denominator.
Okay.
Yeah. If you get confused, don't do it directly. Do it with the steps what we had done in the very first question, like this.
Okay. Okay.
Okay.
Okay. Actually, here we are taking out the negative of denominator and then positive of numerator, ma'am.
Yes.
Okay. Thank you.
Yeah. Okay. Any other questions? Okay, if not, then let me move on to the next question. So the sixth question says that you are given this again same transfer function and want to find its parallel form 1 and parallel form 2 representation. So the parallel form representation is basically you have some h1 plus h2 kind of system and you want to connect them in parallel. Now what happens is you here I have written parallel form 1 and parallel form 2 representation. So for parallel form 1 we do partial fractions with respect to z inverse, and for parallel form 2 we do partial fraction representation for using z. When I mean you map the transfer function as a function of z instead of z inverse and then do the partial fractions. It will become clear when I solve a particular example, this particular example. So you have h of z. So first I'll do parallel form 1. So we have h of z, which is equal to 1 plus 2z inverse upon. In the previous question itself, we have seen that we can factorize the new denominator as 1 minus 2z inverse into 1 minus z inverse. So now we can get the partial fraction representation something like this. That is a upon 1 minus 2z inverse plus b upon 1 minus z inverse. So therefore, if I cross multiply, I'll get 1 plus 2z inverse, which is equal to a into 1 minus z inverse plus b into 1 minus 2z inverse. So case 1, when your z inverse is equal to 1, so that will give me 1 plus 2, which is equal to a into 1 minus 1 0 plus b into 1 minus 2, that is minus b. So therefore your b comes out to be equal to minus 3. And second case is you want to nullify this particular factor in order to get your a. So in order to nullify this, your 2z inverse should be equal to 1 or your z inverse should be equal to half. So z inverse equal to half. That will give me 1 plus 2 into half, which is equal to a into 1 minus half plus 0. So that will give me 2, which is equal to a by 2, or in other words, I get a equal to 4. So therefore, h of z comes out to be equal to, it was a upon 1 minus 2z inverse, so a is 4. So we have 4 upon 1 minus 2z inverse plus, I have minus 3, that is b, minus 3 upon 1 minus z inverse. So this is your h1 of z and this is your h2 of z. So we are going to represent this as something like this, h1 of z, h2 of z, and then add. And this is effectively your capital H of z. And you're uh, connecting h1 of z and h2 of z as a parallel combination. That's why this is referred to as parallel representation. So let us first represent your h1 of z. So let me do color coding a little bit here. Okay. Yeah. So let's start with h1 of z. So you have an input here. Then you get, okay, let me not do it like this. Okay. Since you are getting a scaling in the numerator, I'll do it properly for this for the first time. Okay, so let's do h1 of z. So h1 of z which is, let's say, y1 of z. Note that both of them have same input, x of z, which is equal to 4 upon 1 minus 2z inverse. So you have y1 of z into 1 minus 2z inverse, which is equal to 4 into x of z. So you get y1 of n minus 2 times y1 of n minus 1, which is equal to 4 times x of n. So you have y1 of n, which is equal to 4 times x of n plus 2 times y1 of n minus 1. So you have y1 of n, which is equal to 4 times x of n plus 2 times y1 of n minus 1. So we'll do direct form 2 representation. So first we will construct this. So you are here, something like this. So you have a z inverse. So first we will construct this denominator or output part. So this is basically your delayed version. So you will get a 2 here, like this, and you have 4x of n. So this corresponded to your x of n wala thing. So this gets multiplied by a factor 4. If this is incomprehensible right now, I'll do direct form 1 first and then map it back to direct form 2. So just a small digression. If you have direct form 1 representation of this is your x of n. Now do you have x of n, or you have 4 times x of n? So you have 4 times x of n, and this gets added to what? This gets added to 2 times y of n minus 1. Your output is y1 of n. This gets delayed and it gets scaled by a factor of 2, and it gets added like this. Okay, now swap this and this. So this will come first here, and then this will come after that, like this. So if you look at this particular part and this particular part, they are same. And if you look at this part and this part, they are same. Is it clear now? Now in similar way, this particular system, whatever we did now was your h1 of z. In similar way, we can do h2 of z. H2 of z is minus 3 times 1 minus z inverse. So we'll start with the denominator. So for denominator, you have a 1 here. So this 1 is as it is here. Then you get a delay, and then you multiply this again, the direct form 2 representation. You have minus 1, so that will become a plus 1 here. You will add it here, and your input is scaled by a factor of minus 3, so you will get a minus 3 delay block like this. So this is basically your H2 of n. Again, For better understanding, let us first do your direct form 1 representation also. So how does your direct form 1 representation look like? You'll start with your x of n, and then you will have a scaled version of this by a factor of -3, and then that has to be added with something. That has to be added with your y of n to get y of n, y2 of n, a scaled version of this multiplied by a factor of 1, and that gets added like this. Now again, this part is your this part, and this part is your this part. So this particular thing is here, and this particular thing is basically this. So this is your denominator representation, and this is your numerator representation. So in direct form 2, you first represent your denominator and then you represent your numerator like this. Okay. So now you have h1 of z and you have h2 of z. So now you can just connect both of them in parallel. So your h of z looks something like this. So you have x of n, you have the representation of your h, sorry, yeah, you have first the representation of your h1 of z, which is something like this. So you have an adder block, you delay it, and multiply it by a factor of 2 and add it, and you scale this by a factor of 4, and this is your y1 of n. Similarly, you have an h2 of z, you have an adder block, z inverse, you scaled it by a factor of 1, and this gets scaled by a factor of -3, and this basically gives you your y2 of n. And your y of n is what? Your y of n is basically y1 of n plus y2 of n. So you have an adder block. You add both of these outputs to get y of n. So this is basically your parallel form 1 representation. So in this particular question, I did each of these one by one to this level of detail. I won't do it for the second. If you get confused, then stop me and ask. I'll do it. This is for your practice. Okay, any questions till this point? If not, then I'll move on to the parallel form 2 representation of the same system. So we had to do both parallel form 1 and parallel form 2. We have just completed the parallel form 1 representation. So let's start with parallel form 2. So parallel form 2. In this, what do we do? In this, we basically represent your system h of z as a function of z instead of z inverse. So we have h of z, which is equal to 1 plus 2z inverse upon 1 minus 3z inverse plus 2z to the power minus 2. So we can write this as z plus 2 divided by z whole divided by z square minus 3z plus 2 divided by z square. So this gets cancelled, and what we have, z into z plus 2 upon z square minus 3z plus 2. So therefore I can rewrite this h of z as z square plus 2z divided by z square minus 3z plus 2. This I can write as z square minus 3z plus 2. I added minus 3z and plus 2z, so I can just subtract them, plus 3z minus 2, and you already had a 2z here, like this, whole divided by z square minus 3z plus 2. Why are we doing this? We are doing this because in order to get partial fraction representations, the degree of your numerator should be less than the degree of your denominator. And it was not the case in this particular first part. So this is equal to 1 plus 3 plus 2 is 5z minus 2 divided by, you can factorize the denominator as z minus 2 into z minus 1, like this. And now you can consider this particular part for partial fraction representation. So you have 5z minus 2 divided by z minus 2 into z minus 1, which I can write as c upon z minus 1 plus d upon z minus 2. If I cross multiply and cancel out terms, that will give me 5z minus 2, which is equal to c times z minus 2 plus d times z minus 1. Okay, so now first thing, z is equal to 1. That will give me 5 minus 2, which is equal to c minus 1. So 5 minus 2 is 3, which implies c comes out to be equal to minus 3. And when you have z is equal to 2, you get 5 into 2, 10 minus 2, which is equal to c into 0 plus d into 1, which implies that here d is equal to 8. So what do we get? So we have h of z, which is equal to 1 plus c upon z, c upon z minus 1 plus d upon z minus 2. Just a moment. Okay. So this I can write as 1 plus, I can multiply and divide by z in the z inverse in the, or rather I can divide by z in the numerator and denominator. That will give me minus 3z inverse divided by 1 minus z inverse, plus I'll have 8z inverse upon 1 minus 2z inverse. Okay, so this is like 1 plus h1 of z plus h2 of z. So now we'll start with h1 of z, h2 of z again. 1 is anyway 1. We can't do anything with it. So let's start with h1 of z. h1 of z is what? Minus 3z inverse upon 1 minus z inverse. So let's start. We'll first do the denominator. So for denominator, we first get an adder block. We are doing direct form too. of n, and then for this 1 we already have it here, z minus 1 z minus z inverse. So first we'll do a z inverse, and then we'll do a 1 like this. So this is the denominator. Now in the numerator, what do we have? We have minus 3z inverse. So we want to add, or yeah, okay. Yeah, we have this particular thing here. Okay, so I am also getting confused here. Let's do it one by one now. Just start with direct form 1. This is confusing for me. Okay, so you have h1 of z, which is y1 of z equal to minus 3z inverse upon x of z. So you have y1 of n, which is equal to minus 3x of n minus 1 plus y1 of n. Okay, you have x of n, z inverse minus 3, this gets added, z inverse, then you have y of n minus 1 like this. This is your y of n. So you have this block here, and from this z inverse, now you will pull out a minus 3. So that will basically give you a minus 3z inverse, and you'll measure your output here. So I just swapped this system and this system here. So this part is this part, and this part is this part. Is it clear? Any questions? Okay. Similarly, you can construct your h2 of z. h2 of z will be in similar fashion. So your h2 of z is basically h2 of z is 8 z inverse upon 1 minus 2 z inverse. So you have, first we'll construct again the denominator. Now this will be very similar to what we have here with different gains. So you scale it, z inverse. You have minus 2 here, so minus minus plus, and add it like this. And then you scale this part by 8, that is your input, and you get your y2 of n. So this part is 1 minus 2z inverse, and this part is basically your 8z inverse. This is your numerator part. This is your denominator part. Okay, so now you have h1 of z, h2 of z. What your h of z is what? Your h of z is 1 plus h1 of z plus h2 of z. So you have your x of n, you have a 1, then you have h1 of z. h1 of z looks something like this. So you have an adder block, Z inverse, and delay block, gain block of factor 1. This gets added, and you have a minus 3 here, which is basically your y1 of n. Similarly, you have an adder block. Let me just pull it up a bit. You have an adder block. Now I'm generating h2 of z. Same way, z inverse. Then I have a gain block of 2 units. Again, here I have a gain block of 8, and that basically gives me y2 of n. Now this gets added here, and this is basically your y1 of n plus y2 of n. That also gets added with 1. So this is basically 1. So this is your parallel form 2 representation of this particular system. So this is parallel form 2 representation. Is it clear? Any questions? Okay. If not, then let's move on to the next question. So the next question, again, now we'll take up another transfer function and repeat all those 7 forms that we have already seen. So we'll start with the direct form 1 and direct form 2 representation, but the transfer function now given to us is something like this. So h of z is 1 plus 2z inverse plus z to the power minus 2 upon 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2. So let us first do the direct form 1, and then we'll do direct form 2. So for direct form 1, what do? We first construct the numerator polynomial. So here you have x of n, you have your x of n, then you have 2z inverse. So first you get x of n minus 1 by z inverse. That gets scaled by a factor of what? 2. Then you have z to the power minus 2. So again you will z inverse, delay your x of n, then you get a gain block of 1, then you add this. Here you get x, at this particular point you get 2xn minus 1 plus x of n minus 2, and then you add it to your x of n. So this completes the construction of your numerator polynomial. Now for denominator, you have your y of n here. This corresponds to your y of n, 1. Then you multiply. Then you have minus 3 by 4 z inverse. So you have z inverse, and you multiply it by a gain of minus 3 by 4, and while constructing denominator you take minus sign of the coefficient. So this will be 3 by 4. Similarly, you have z to the power minus 2. Yeah. And you scale it. You have a 1 by 8 here, so you will scale it by minus 1 by 8. And you add it. So here you will get your minus 3 by 4 yn minus 1 and 1 by 8 yn minus 2, and you add this and this to get your y of n. So this is your direct form 1 representation. To get direct form 2 representation, you swap these two and combine your gain delay blocks. So you have x of n, then you have two delays, like this. The first block here will be of 3 by 4, and then we'll have minus 1 by 8. This gets added like this. Then from this delay, we'll pull out this branch. That is, you have 2. And then from this delay, we'll pull out this particular branch. And you'll simply add these two to get your output y of n. So this is your direct form 1 and direct form 2 representation of this particular system. Okay. Let's move on to the next question if there are no queries. So the next question here is same thing, but now with direct form 1 transpose and direct form 2 transpose. So what do you have? You have your h of z as 1 plus 2z inverse plus z to the power minus 2 divided by 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2, which I can write as wz upon xz into y of z upon w of z. So again, same trick I'll do. I'll write this as 1 upon 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2 multiplied by 1 plus 2z inverse plus z to the power minus 2. So this is basically your h1 of z, and this is basically your h2 of z. Now I'll just write it down. I have w of z upon x of z as 1 upon 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2, and you have y of z upon w of z as 1 plus 2z inverse plus z to the power minus 2. So I'll first do direct form 1 transpose. So we start with x of z, x of n, like this. And what we do is we first multiply. So this is your w of n. So what we do is we first multiply by the gain, and in order to reduce the number of things blocks, we'll multiply it here. So you will get, so this is in the denominator, so every time when you have anything in the denominator, you will get a plus, you will get a flip sign, and then you will delay it by 1 unit like this. Similarly, you have z to the power minus 2 into 1 by 8. So you'll have minus 1 by 8 z inverse like this. Now your y of n is somewhere here. So what you get, you have your w of n as it is getting added, along with you have 2 times z inverse of wn. You multiply this here, so 2 times wn minus 1, and you also have 1 time wn minus 1 again delayed by 1 unit, that is wn minus 2, something like this. So this is your direct form 1 transpose representation. And in order to get direct form transpose 2 representation, what we do, we flip or we swap these two systems. So basically what we will do for direct form 2, we will start with this point, or rather we first construct this. So we have x of n, then I'm just taking up this particular block. This gets delayed by 1 unit, and then you have z inverse like this. And finally you will take up this block, and since this z in this adders are common, we just need to take into account this part now. So you have y of n, this is of 3 by 4, and this is of minus 1 by 8. You have a adder here. Okay, so this is your direct form 1 transpose and direct form 2 transpose. Okay, if no questions, then let me move on to the next part, that is the cascade representation. So for cascaded representation, again we'll write it in terms of h1 of z into h2 of z, and we'll take 2 blocks and then cascade them. So you have h of z equal to 1 plus 2z inverse plus z to the power minus 2 whole divided by 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2. The numerator can be factorized as 1 plus z inverse whole square, and the denominator can be factorized as 1 minus half z inverse into 1 minus 1 by 4 z inverse. Okay. Okay, so now we can write this as 1 plus z inverse upon 1 minus 1 by 2 z inverse multiplied by 1 plus z inverse upon 1 minus 1 by 4 z inverse. So this is basically equal to h1 of z into h2 of z. Okay, so now what we want to do is we want to do something like this: h1 of z, H2 of Z. So let me just quickly write both of them. H1 of Z is equal to 1 plus Z inverse upon 1 minus half Z inverse, and H2 of Z is 1 plus Z inverse upon 1 minus 1 by 4 Z inverse. So your H1 of Z will first represent your H1 of Z. Again, we'll use direct form 2 for representing H1 of Z and H2 of Z. So for H1 of Z, let us first start with the denominator part. So you get an adder block and then you have a 1 here, then that gets delayed by 1 unit, and you have in the denominator a scaling of minus 1 by 2. So that translates to, since it is in denominator, it changes its sign and you get something like this. Now for the denominator, you have a 1 coming from here, and you have plus Z inverse, so something like this from here. So this is basically your H1 of Z. And in similar way, we can construct H2 of Z. Again, we'll start with denominator. So we'll have this adder block. Then you get a delay of 1 unit, 1 by 4. You have minus 1 by 4 here, so that gets converted to 1 by 4. Flip the sign and you get something like this. Now in order to construct numerator, you have 1 plus Z inverse, so Z inverse and a gain of 1 like this. So this was your H1 of Z. This is your H2 of Z. Input is X of n, your output is Y of n, and in order to connect them in cascade, we just need to connect them like this. Okay, so effectively what you get here is your H of Z. Is it clear? Any questions? Okay. Okay, if there are no questions, then let me move on to the last question that I have planned to cover today. So it is again for the parallel form 1 and parallel form 2 representation. So we have H of Z. So in this particular question, what I'll do, I'll first get the transfer functions for both the systems. And okay, let's start with parallel form 1. It's fine. So for parallel form 1, you get partial fraction representation in terms of Z inverse. So you have H of Z, which is 1 plus 2Z inverse plus Z to the power minus 2 divided by 1 minus 3 by 4 Z inverse plus 1 by 8 Z to the power minus 2. Now what you do, again you have numerator and denominator having same degrees. So I'll write it in this form: 1 upon 1 minus 3 by 4 Z inverse plus 1 by 8 Z to the power minus 2 plus Z inverse. I can write it as, or 2 plus Z inverse Yeah, okay, let's do it in this way. Upon 1 minus 3 by 4 z inverse plus 1 by 8 z inverse. Yeah. Okay, so we have this now. I'll add a blank page.
And
Let's not do it.
you get that minus 2.
Sorry?
Okay, ma'am.
Sorry. Yeah, no, I don't want to do it in this way. I'll again add and subtract minus 3 by 4 z inverse and 1 by 8 z inverse. That simplifies many things. Plus 1 by 8 z to the power minus 2 plus 3 by 4 z inverse minus 1 by 8 z to the power minus 2, and you already had 2z inverse plus z to the power minus 2 as it is, divided by, I can factorize the denominator as 1 minus 1 by 4 z inverse into 1 minus 1 by 2 z inverse. Okay, so the first term here will give me a 1 plus, for z inverse you have 3 by 4 plus 2, so that will give me 8 by 4. Sorry, 8 plus 3, that is 11 by 4. So you'll have 11 by 4 z inverse plus you have 1 minus 1 by 8, that is 7 by 8 z to the power minus 2 whole divided by 1 minus 1 by 4 z inverse into 1 minus 1 by 2 z inverse. So that I can write it as 1 plus z inverse into 11 by 4 plus 7 by 8 z inverse whole divided by 1 minus 1 by 4 z inverse 1 minus 1 by 2 z inverse. Now what I'll do is I'll just take up this particular part and use partial fraction representation. So I have 11 by 4 plus 7 by 8 z inverse whole divided by 1 minus 1 by 2 z inverse into 1 minus 1 by 4 z inverse, which will be equal to a upon 1 minus 1 by 2 z inverse plus b upon 1 minus 1 by 4 z inverse. So we get 11 by 4 plus 7 by 8 z inverse, which is equal to a into 1 minus 1 by 4 z inverse plus b into 1 minus 1 by 2 z inverse. Now, in order to nullify z in the coefficient of b, let z inverse to be equal to 2. So what we get is 11 by 4 plus 7 by 8 into 2, which is equal to a into 1 minus 1 by 2. So this gives me 18 by 4, which is equal to a by 2, which implies that a comes out to be equal to, this gets cancelled, and 9. So a comes out to be equal to 9. Similarly, in order to cancel the coefficient of a, z inverse should be equal to 4. So that gives me 11 by 4 plus 7 by 8 into 4, which is equal to a, this gets cancelled, b into 1 minus half into 4. So therefore I'll keep this 4 as it is. So this is 14 plus 11, that is 25. So 25 by 4 will be equal to b into 1 minus 2, that is minus b. So in other words, b comes out to be equal to minus 25 by 4. So therefore, what do we have now? A is 9 and B is minus 25 by 4. If I plug in all of this in my h of z equation, what I get is h of z to be equal to, this 1 is as it is, 1 plus z inverse. Inside the bracket I have a upon, a is 9, upon 1 minus half z inverse plus b is minus 25 by 4 upon 1 minus 1 by 4 z inverse. So in other words, I can write h of z to be equal to 1 plus 9z inverse upon 1 minus 1 by 2 z inverse plus minus 25 by 4 z inverse upon 1 minus 1 by 4 z inverse. So again, let me color code this. Yeah. So 1 is as it is, then you have, this is your first system, this is your second system, and this is your third system. So 1 will remain as it is, whatever you have. Yeah, so you have a 1 here. Then you have the second system, which has the same input as x of n. So we'll first construct the denominator. You get an adder block first. Then you have a z inverse. And you have a gain of half to 1. And then you have a 9z inverse, which will be pulling out from here. So this will give me a 9z inverse. So this is basically the output of my first system. Yeah. So this is basically y1 of n. And similarly, I can construct my second system. So I'll have an adder block, a delay block for denominator's delay, and you have a 1 by 4. So you will get 1 by 4. This gets added here. And you get in the numerator, you have minus 25 by 4 z inverse. Z inverse is already there, and you get a minus 25 by 4. Something like this. And this is basically your y2 of n. Your y1 of n, so you now have your 1, you have your x of n, you have your h1 of z, and you have your h2 of z. So basically you have a common input to all of this. So this is your x of n. So this is like this. And your this system gets added, the outputs of all of these get added. And this also gets added. So this is your parallel form 1. Representation. Is it clear? Now in similar way, we can do parallel form 2 representation. But in order to do that, we need to consider our transfer function in terms of z. So now we'll do parallel form 2 representation. For that, we can have h of z to be equal to 1 plus 2z inverse plus z to the power minus 2 divided by 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2, which you can equivalently write as z square plus 2z plus 1. I'm just multiplying and dividing by z square. So I'll get z square minus 3 by 4z plus 1 by 8. So this again I can write it as z square minus 3 by 4z plus 1 by 8 plus 3 by 4z plus 2z minus 1 by 8 plus 1 whole divided by z minus half into z minus 1 by 4. So the first term gets cancelled, plus you have 3 by 4 plus 2, that is 11 by 4z, plus you have 1 minus 1 by 8, that is 7 by 8, divided by z minus half into z minus 1 by 4. So now I'll take up the second term and get partial fractions representation of that. So we have 11 by 4z plus 7 by 8 whole divided by z minus half into z minus 1 by 4, which is equal to a upon z minus half plus b upon z minus 1 by 4. So we get 11 by 4z plus 7 by 8, which is equal to a into z minus 1 by 4 plus b into z minus half. Now let's say z is equal to half. That will give me 11 by 4 into 1 by 2 plus 7 by 8, which is equal to a into half minus 1 by 4, that is minus 1 by 4. Yeah, so that will give me, this is 18 by 8, which is equal to minus, sorry, not minus, plus 1 by 4, a by 4. So this just gives me a is equal to 9. Similarly, if I put z is equal to 1 by 4, that will give me 11 by 4 into 1 by 4 plus 7 by 8, which will be equal to b into 1 by 4 minus half, that will be equal to minus 1 by 4. So that gets cancelled. Okay, leave it. Yeah. So what do we have? So basically, okay, so we have 11 by 16 plus 14 by 16, which is equal to minus b by 4. So we get a 4 here. So therefore b comes out to be equal to minus 25 by 4. So what do we have? Therefore h of z comes out to be equal to 1 plus a is 9 upon z minus half plus minus 25 by 4 z minus 1 by 4. Now I can again write this as 1 plus, I can multiply numerator and denominator by z inverse. So that will be 9z inverse upon 1 minus half z inverse plus minus 25 by 4 z inverse upon 1 minus 1 by 4 z inverse. Now if you compare this particular equation with the equation that we saw here in the first parallel form, so both of them are same. So I'll just number this as 1 and 2. So 1 and 2 are same, which implies that the parallel form 1 and parallel form 2 representations are identical or same. Is it clear? Any questions? So this is all I wanted to cover today. If you have any questions in any part of today's tutorial or in this particular question, please feel free to ask. Otherwise, thanks for attending today's session and you're free to leave the meeting. Again, just a quick reminder, Sunday 3 p.m. we'll have a summary session. NPTEL people will float an announcement regarding that along with the meeting link, which is essentially the same link with which you joined today. Okay, so I'll take up most probably a revision, and if you have any queries, then just post it in the Q&A portal by tomorrow 12 noon. Okay, so if you have any other questions, then please ask. Otherwise, you can leave the meeting. Again, thank you for attending today's session and hope to see you all on Sunday as well. Thanks.
Thank you, ma'am.
Thank
Thank
you.
you, ma'am.
Ma'am, on request, ma'am,
Yeah.
is it possible to take a region of convergence, ma'am, both for Laplace and Fourier transform?
You want me to explain region of convergence?
Yes, ma'am. Yes, ma'am.
Is it okay if I do it in the summary session? I'll do it.
Okay, ma'am. Thank you.
Yeah. Okay. I'll discuss the region of convergence there. I'll discuss it.
Okay,
Yeah.
ma'am. Thank you, ma'am.